All right, let's look at some applications of work energy theorem. So just to remind you, work can be turned into energy, which is the potential to do work. And if you have potential energy, then you can tap that to get more work out the other end, right? The laws of the universe say that no energy is ever lost, okay, in this process. However, it may not all make it from one form to another due to losses to things like heat and so on, okay? And this is essentially like, your laws of thermodynamics, like energy is conserved, but it's not all available due to losses to the environment, okay? So we're going to look specifically at types of energy. Where can we store energy? So just as a reminder, our definition of work is F d cos theta. Okay, so that's our definition of work. And you need energy in order to apply a force over a distance, right? That makes sense. If I want to push something, I got to have a store of energy to allow me to do that, okay? For instance. So the first kind, the easiest to understand, and we'll use this nomenclature where E represents a pool of potential, and then a sub script will indicate the type. So the first type we're going to talk about is gravitational potential energy and some of its applications. And so just to define this, and we've danced around this quite a bit and actually kind of used it to help us define work to begin with. But let's say we have some mass, right? And we'll grab a little mass here. Okay, and let's just give this a mass of, I don't know, let's say 10 kilograms. Well, we know the gravitational pull on that, the weight if we want, or the Fg, okay, is equal to just m times g. So what that means is the upward force required to keep this thing sitting still or moving at a constant velocity is equal and opposite to this value, okay? Now, if we ignore the little bit of extra force that we need to accelerate this to get it moving, we just say it's already moving when we start, then what we'll know is that we need to apply a force over a distance, so a force that's equal to g, right? Because we want to maintain that value of 0, right? An F net on this thing equal to 0, and then it will move over this height, right? This height here. All right, so Fg times height, okay, we'll get this ball from down there on the ground to up here some height above the ground, right? So we've had to work to do that, right? We've had to apply a force, and it's just a constant force, so it's nice. The math is easy. It's not a changing force. It's just a constant, consistent force over this height, okay? So then we say, all right, well, Fg is equal to mg. So in order to just look at an object that's raised above the ground and say, in order to get it there, we had to apply a force over a distance, right? Force times d. But just to clarify that we're talking about Eg, we're just going to slightly rewrite this. We're going to acknowledge that force is made up of m times g, and that we're calling the distance now height, right? And it's in a straight line, right? The force isn't acting at an angle, so that cos theta just is 1, right? So we get this, m, g, h, right? There's my mg, and there's my height. So any object that's raised some, distance above the ground has the potential to do work, right? If I've got it up here and I let it fall, it's going to race back towards the earth, and it will, it can do stuff for me. Like if I hook it up to a pulley system, I can get it to do work in another direction, right? I can make it pull some object this way. I can make it run a cuckoo clock. I can use it to raise an elevator and so on and so forth. Okay, so pretty straightforward. Let's do some work with this now. Let's bring back something that we dealt with before. Let's figure out a couple of things here. So I want to get a box up here, all right? So let's create a box here. Okay, so there it is. Let's give this a little bit of an angle. Let's call this 30 degrees, okay? And let's say this height is, I don't know, 10 meters, okay? Now there's two ways we can get the box up to the top here, right? We could lift it straight up, or we could push it up around, okay? And let's just say, for argument's sake, that this is a frictionless surface, okay? I don't know how I'm pushing it, it's frictionless, but let's say it's frictionless. So this is what I want you to do, okay? I want you to look at this in two ways. Okay, A, how much work is required to move the box to position, I don't know, let's call it alpha, to position alpha from ground level. Okay, and what I want is I want it proved two ways. A, proved using direct lifting, and B, proved using sliding up the ramp. Okay, so both will achieve the same result, right? My box will be, you know, up on some higher platform, okay? But I either pick it up and lift it straight up. I must be really tall if I'm lifting it 10 meters, but you get the point, right? Or I push it up a ramp, right? Because it'll, in both cases at the end, my box will be at the top of the ramp, okay? So I'll let you just wrestle with that for a second, and then we'll solve it both ways. And then we're gonna have a part B. And part B is, which way is easier and why? And one important piece of information is, how much does this box weigh? Let's make it like 100 kilograms. It's heavy. All right, so let's have a look at this. We'll first look at the direct lift. Okay, how much work is required for the direct lift? So if my box is here, weighs 100 kgs, the first thing I need to do is calculate what its weight is. So Fg equals mg. I'm just going to use 10 for g, just because it makes it easier. So what that does is it gives us a weight of about 1,000 newtons, roughly 1,000 newtons, right? 100 times 10 is 1,000. So I'm going to need to, in order to lift it, apply a 1,000 Newton force, right, times 10 meters. And I should get 10,000 joules in order to lift it up here. Okay, so 10,000 joules are required to lift that up here. And what that's also saying now is that I've stored the potential to do 10,000 joules worth of work upon this returning to the ground, right? If I either drop it or let it come down the ramp. So now, if we think about it, we have a fairly large force here, and we're moving over a pretty short distance. So when we think about what's going on the ramp, it's slightly different here. Let's have a look at what it's going to be like. So I'm just going to grab the box and I'm going to place it on the ramp so we can analyze what's going on with it. So while it's on the ramp, it's going to have a force that is, or require a force, I guess, that's related to the angle on the ramp, right? So earlier on, we learned that the force of gravity aims down, right? There's a normal force on here in this direction, okay? And then there's a force parallel to the ramp in this direction, okay? We also learned that this angle theta here is equal to 30, right? It's equal to this value here. They're the same angle. These are equal triangles, or similar triangles, I should say. And then we know that this side here, right, that's the force of gravity, so that's equal to mg. So in this case, that'll be 1,000, right? Because it's the same weight, or the same box. And then we know that Fa, that's the force tending to send this down the plane, is found as mg, right, the hypotenuse, times the sine, is with the opposite angle, the sine of theta. So the amount of force then required to keep this moving constantly just has to be equal and opposite to FA, right? So this is the applied force that we're going to put on there. We'll put it as FP. The amount of force that's going to be required to just push this up the ramp, okay? Because we're frictionless, we don't need to worry about any friction in this scenario, okay? We'll talk about what happens with friction later. Now this amount, right, is going to be lower than 10,000, isn't it? Because it's just a part of this triangle. We know that this is where your, less than 1,000, my bad. This part is where the 1,000 lays. So let's actually figure out what we get for FA. So FA then is equal to mg sine theta. So we know mg to be 1,000. So 1,000 times the sine of 30 degrees. So we get then that that force is equal to 500 newtons. Okay, that force is equal to 500 newtons. So you only need to apply 500 newtons worth of force rather than 1,000. Okay. However, if conservation of energy and conservation of work and work energy theorem and all of that is true, you should still require the same amount of work to get up there, right? Because no matter how you got up there, you should have the same amount of gravitational potential. So the explanation for that is that now this has to be applied over a much larger distance. So we want to know, what is the distance of this hypotenuse here, right? How far do we have to push this object in order to get it up there, right? So how do we actually calculate that? Well, if we have this angle, right, and we know that this is 10 meters, then we should get this. D should be equal to 10 meters divided by the sine of 30 degrees, right? So 10 over sine 30 should be 20 meters. So this distance is 20 meters. And aha, now something interesting should happen. Whether I lift it straight up, right, I get 10,000 joules. We saw how to do that. And that's just found as mgh. Or we figure out how much force is required on a slope. So in this case, it's 500 newtons. However, it's times a 20 meter. At the end, we still get 10,000 joules worth of work is required to get that up the slope, right? And then no matter how I got it up there, it still contains that amount of potential energy. So this is kind of interesting because now what we're looking at is one of the simple machines that you would have learned about way back when, which is a ramp or a wedge. And the use of this is that it allows you to apply less force to give something gravitational potential energy than would be required if you were just lifting it straight up. So you can't get out of doing work because the same amount of work is done in both cases. However, one is done with a high force over a short distance, and the other is done with a lower force over a longer distance. So you can imagine that as you lengthen this ramp longer and longer, the amount of force required gets lower and lower. However, the distance you need to push your object over gets higher and higher. So you can't get free work, but you can get work done with less force by elongating the distance. And this is often how simple machines are set up. You can think about this if you know about pulleys or you know about other ramps and so on. So again, the ramp is an easier way to give something potential energy because less force is required. Less force needed. Humans are like, you know, we're only as strong as we are, so we've devised methods to magnify, if you want, to not necessarily to magnify the force, but to pay for our work by increasing distance and lowering the amount of applied force necessary. You can kind of think about things like maybe like a lever and how it would do that, right? Ooh, that's not a straight line. So like, let's say I had a lever here, right? Okay, and I want to lift something heavy that I couldn't lift directly. Big box, say, right? You see that if I move that lever on this end this far, right, it only moves, right, like this far on this end. However, the amount of force applied over here, and I should actually move this over a bit so it makes more sense. Actually move this like this. Okay, there we go. The ratios of distance here, and it's kind of interesting. I mean, the Greeks knew this, but the ratio of of this distance to this distance is actually going to give you the ratio of applied force here to applied force here, but just the inverse of it, right? The longer this is, the higher the force over here is. However, the longer this is, the farther you have to move this end, right? F times D. So we have low force long distance to give us high force over short distance. Okay, does that make sense? This is a conservation of energy scenario, but it's a way to do work that we wouldn't maybe normally be able to do because we're too weak to directly lift it. So we devise ways, ramps, levers, pulleys, screws, etc., to do work we couldn't normally do, right? So I want to move on from this concept to another work energy theorem scenario, and that is kinetic energy. So this is the energy that you would have in any mass with motion, with a velocity, right? So if something is massive and has a velocity, it can do work for you. Think about it. If you whip a heavy object, a bowling ball or a mass or a weight at, say, a thumbtack, right? I love the thumbtack, right? Because you can apply a force over a distance to drive something like this into the wall, and I just assume that it's a constant force, right? So if we have an object with mass that has a velocity, it could do work for us, okay? Another interesting thing is, if I do have an object with gravitational potential, and I let it roll down a slope, well, it's going to convert its gravitational potential into a rolling ball with motion, right? So its velocity will be high after I let it roll down the slope. So this is a way that I've taken gravitational potential and I've turned it into the new kind of potential energy, which we call kinetic energy, or kinetic potential energy. Some people might call it that. So just E sub k. So another form of stored energy. So we're going to use, again, work energy theorem to talk about what happens if I take an object and I apply a force to it over some distance, and how we can then figure out what kind of energy it has at the end. So let's imagine this, right? We've got a ball. Let's say it's starting at stock still relative to us. So it's an object, it's sitting still. B equals 0. And then I start to apply a force to it by, say, pushing it. So a force is now applied. And that force, because we have a mass here, will accelerate, right? It'll accelerate. It'll speed up. And it'll cover some distance. We'll call that, how about D? Okay, some distance while it's accelerating. And eventually, it'll be somewhere down the track, but now it'll have a higher velocity, right? So it'll have a V, and let's call this V naught, right? It'll have some velocity now that is obviously greater than V naught. We'll say no friction involved, right? No friction. So I have a perfect conversion. So did I do work in moving this object along? Sure, okay? So let's just remind ourselves that work can be converted into potential energy, and that our definition of work equals force times a distance. Now, I'm going to leave the costate off of here right now because we are pushing in the direction of motion, okay? You can put it back on later if you want. Now, let's think about this. Another way to talk about force is in terms of Newton's second law, which is just ma, right? So work equals ma d. The amount of work I did is force times distance, or it's mass times acceleration, mass times acceleration times the distance we moved over. Do you agree with that? Okay, perfect. We also have a handy little formula that says v squared equals u squared plus 2 times ad. Actually, sorry, you guys don't use u squared, do you? You use vf and vi. My bad. Vf and vi. Okay. So we have this. Now, what was the initial velocity of this object? What would we say it was? And 0 squared is just 0. So let's get rid of that. So we could say this, couldn't we? We could say that vf squared divided by 2 equals a times d. Or we could say 1/2 v squared, right? Let's leave it as v squared for ease sake, right? It's the final velocity, we know that. And then we can look over here and say, okay, my little formula over here has an AD in it, doesn't it? So then I can do this. The amount of work I did will be converted into energy of motion of that object rolling along, EE, which is equal to M, and we're going to replace AD with 1/2 v squared, and we're just going to rearrange and we're going to say this. And I don't know why I have an E there, it should be a K, my bad. It's kinetic energy. Kinetic energy. The kinetic energy is equal to 1/2 the mass times the square of velocity of the object that I'm pushing along. Okay, so, I mean, we could do some fancy stuff with this, but let's just, let's do something simple. Find the energy, I'll say the potential energy. Potential energy, or the amount of work that a 10 kilogram mass moving at 10 meters per second has. And then we're going to change it. What if I double the speed? Okay, so now do the same thing, A, 10 meters per second, and B at 20 meters per second. And then C, a 20 kilogram mass at 10 meters per second. Okay, so let's crunch numbers here. So we've got 1/2 mv squared. I feel like a different color maybe. So we've got 1/2, 10 kgs, 10 meters per second. We'll square the whole thing. So 100 times 10 is 1,000 times 1/2. We should have 500 joules here. Okay. I'm going to skip to C and do it first. So 1/2 times 20 kgs times 20. Oh, sorry. Times 10 meters per second. We'll square that. So we've got 100 times 20, 2,000, 1/2. We've got 1,000 joules. So doubling the weight doubles the energy at the same speed. What happens here? We've got 1/2, 10 kgs, but now we've got 20 meters per second, and we're squaring that. So that should be 400, right? So 400 times 10 is 4,000. Half of that equals 2,000 joules. So this is a key thing to realize, that increasing velocity causes energy to rise as a square of that velocity. So in other words, doubling velocity increases potential energy by 4 times. Tripling velocity increases it by 9 times. Going 10 times higher increases it by 100 times, and so on up the pipe, right? I had to think about what 10 squared was. So this is a very important thing to realize, that doubling mass will only double your energy at a given speed, but doubling velocity will quadruple the amount of energy. Now you can kind of like make sense of that in a sense by thinking about momentum versus potential energy, right? Like, let's imagine that you have a bus. Okay, I don't know what a bus might weigh, like say it weighs 30 tons. I don't know if they weigh that, but let's say it does. But let's say it's only moving at like 0.1 meters per second. Okay, well, how much momentum does that bus have? We just have m times v, right? So 30 tons is 30 times 10 to the 3 kilograms, right? So knock one off. So we'd have 30 times 10 to the 2 kilogram meters per second, I believe, or 3 times 10 to the 3 kilogram meters per second. All right. Now, if I had a bullet, let's say I had a bullet with momentum equal to the bus. Momentum is equal to the bus. I don't know if this is going to give us a realistic answer, but let's just say we have a bullet equal in momentum to the bus. And let's say that bullet weighs, I don't know, 20 grams. We got a 20-gram bullet, which is 0.02 kgs. How fast must it be going in order to have this much momentum? Can you figure that out? If P equals mv, V should be equal to P divided by m, so 3 times 10 to the 3 kilogram meters per second, divided by 0.02 kilograms. What do we get for that? So you should get 1.5 times 10 to the 5, right? So, you know, 2 into 3 is 1.5, 2 more orders of magnitude added on, so we get 1.5 times 10 to the 5 meters per second. Now figure out their kinetic energies, okay? So EK of the bus. EK of the bus then is going to be 1/2 its mass, so 1/2 30 times 10 to the 3 times its velocity squared, 0.1 meters per second. Square that. And now find EK of the bullet. 0.02 times 1.5 times 10 to the 5 meters per second squared. Okay, so calculate those values for me and see what you get. So my math gives me a difference between these two objects in terms of their energy, as the bus is only going to have 150 joules, whereas the bullet will have 2.25 times 10 to the 8 joules worth of energy. Now, I don't know if it's realistic to ever have a bullet going this fast, but which would you rather get hit by? Even though they have the same momentum. The bus, right? An extremely high-speed bullet like this would likely just vaporize you. Like, there'd probably be very little left of you if you got hit by this. I mean, I think real bullets travel maybe 400 meters per second or something like that. You can think of the damage that they do. But if you have a bullet with the same momentum, and this is a pretty slow-moving bus, right? It's like 10 centimeters a second. It's just kind of barely moving along. It would hit you and would knock you back, but you could probably walk away from something like that. Whereas getting hit by a bullet traveling this fast, it has such an insane amount of energy to transfer your body, you would likely just cease to exist. You would vaporize into nothingness, okay? So that's kind of an interesting thing, right? Momentum is not the end of the story when it comes to how objects interact with each other. There's other things involved. Velocity makes a big, huge difference, okay? Okay, and last but not least, let's tackle springs. So we know this about springs from experimentation. If we have a little graph, oops, come on, go straight. If we have a graph of force on the y-axis and spring extension, we'll call it delta x on the x-axis, and you stay within the elastic range, you'll get springs with fairly straight lines. In other words, the more force you apply, you linearly increase the amount of stretch in the spring. Okay, so there's this direct correlation between these two values. So force is proportional to the stretch, and the stretch is proportional to the force. Okay. Eventually, if you keep pulling, though, you get this deformation, and your spring will get, be ruined. But within this region here, we call this region Hooke's law, or where the spring obeys Hooke's law. Okay, it obeys Hooke's law within here. There's a linear relationship between these things. Okay. We also figured out that if we look at the formula for these lines, y equals mx plus b form, well, there's no b. When you have zero force attached to a spring, it's got zero extension. So we can get rid of that. And then we can figure out that the slope of this line is dependent on how rigid that spring is, right? We could have very rigid springs like this one, or we could have much like, what would you call them? Weaker springs, I guess. So this is a beefy spring and this is a weak spring, okay? So we get this idea. We get that F is equal to M, and M has a name, and we call it K. That's the spring coefficient. It's higher when this slope is higher, but it stays linear, okay? We say F equals K times X. How far my spring is stretched relies on how much force I have, and they become equal through a coefficient, which just essentially converts the force to what I will get for that particular spring. K is a property, geez, words are hard, property of a given spring. Okay, every spring will have a slightly different K value. Okay, and there can be vast ranges of K values. So what that means is, let's think about this. If I have a spring, okay, and I want to stretch that spring out to a longer value, right? We call this delta X, and every point along here is tied into some force value. So moving it a little requires a small force, moving it a lot requires a larger force, all right? So it's not a linear application of force. Force grows as stretch grows, right? We can see that here. So this makes deriving how much energy we store in a stretch spring slightly more complicated to solve for. But this is what we're going to do. We're going to look at this graph, and we're going to figure out how we're going to deal with this. So if this is force and this is distance, then what we're really after in terms of how much work we did to stretch it is F times the change in distance, right? Or the area under this graph. The area under this graph. So let's think about this. F we defined as being equal to kx, right? So in other words, we could call this distance force, but we could also define it as kx, couldn't we? We could define this as kx. So then the area here becomes half, right? Because for we have base times height divided by half, since we have a triangular area. We get 1/2, okay, base, which is x, times kx. Oops, too many x's. Let's do it this way. We have 1/2 x kx, okay? Or another way, if we collect this all up, is we say 1/2 kx squared. So the amount of work we have to do to make a spring stretch is equal to 1/2 its k value times the distance that we stretch it. So doing work energy theorem then, the energy stored in a stretch spring is just equal to that value, 1/2 kx squared. Okay, so that's a bit of a quick derivation of this, but that's the theory behind how we can figure out how much energy there is stored in a stretch spring if we know k and we know how far we stretched it, because the amount of work we put in to stretch it is now stored and can, as the spring's growing back, replenish that work that we put in. Okay, so a stretch spring is an energy containing mechanism. All right, and it can actually be quite, dangerous. If you've ever seen like the spring on the top of a garage door, it's like this gigantic coil spring. Those things can, like, if they uncoil violently, they can produce enough energy to easily kill you. So these are dangerous things, and when they snap, they go flying, bolts and stuff shoot out of them. So although springs seem like all like fun and games, and you really only deal with fairly delicate springs in your day-to-day, there are springs out there that definitely hold the potential to cause you to die. Okay, so now let's look at some like applications of this. So imagine that you have a pinball machine, right? Hopefully, like, you millennials out there still know what a pinball machine is. Am I right? Am I right? So you pull the plunger back on a pinball machine, and a little ball rolls back, right? So what you're doing here is you're loading the spring with EE equal to 1/2 kx squared. You're pulling it back some distance, delta x, and then you're releasing it, right? And what's it going to do? Well, it's going to transfer that energy into a moving object, isn't it? So we can figure out then that what is going on here is that spring potential energy that we're loading in, we're working on this spring to pull it back, is then being transferred into the motion of a ball. And seeing as how work energy theorem says none is ever lost, we can start to do interesting things, like say the amount of elastic potential, or EE or ES, doesn't really matter, you might see it called both, EE will get converted into EK. And then since you know what these values are, you can say things like 1/2 kx squared will be converted into 1/2 mv squared. So if you know some stuff about the spring, you can then predict, without having to do F equals ma, without having to do kinematics formulas, the final velocity of this ball as it springs off of here, okay? And, that ball could, like, roll up around, couldn't it? So it could turn from EK and as it goes up the ramp, it's going to slow down. But that EK is then going to get turned into gravitational potential energy. So then, you could take spring, turn it into kinetic, and then kinetic into gravitational, into mgh, and so on back down and forward. And eventually, due to thermodynamics, the ball would stop rolling. But in a perfect world, this would just continue forever, right? You'd lose nothing and you'd have a perpetual motion machine. One more thing before we finish. You can also think about inertia in these terms, right? So remember Newton's second law and how it was found. It was found as Galileo dealing with ramps, right? So he rolled a ball down a ramp. If you remember us talking about this quite a long time ago, he rolled a ball down a ramp, and he found that no matter what he did to this end of the ramp, right? If he had this ramp like really steep, he found that the ball would still reach its original height, okay? Minus, of course, some frictional losses, which Galileo was able to, account for. But basically he said, no matter what, the ball will always reach its original height. Why did it do that? Let's go back to this. Okay, so no matter what I do to this ramp, that ball will reach its initial height. Okay, and he said, if it can't reach its initial height, it will just continue on forever. We know this as inertia now, right? We say the ball will roll forever unless a force acts on it. But we can also think of it as a conservation of energy scenario, right? If energy can't leak to the environment, we go gravitational to kinetic, back to gravitational, and we'll roll back and forth, and we'll continue this rolling forever, regardless of the height of the ramp. And if we load it with gravitational potential energy, that gravitational potential energy will become kinetic energy, and that ball will just continue rolling forever until we spend the kinetic potential energy, like apply a force against its roll over a distance. So you have to work to make the ball stop. Okay, so this is sort of another way of looking at Newton's laws and kind of thinking about them back towards how energy is sort of the underlying idea in the mechanics of the universe, right? So we start with Newton's laws, we start with forces, and then we build up into how are these forces, doing work for us, storing energy, and then being converted back and forth between each other, okay? There are other pools of potential energy. We could have electrical potential, right? We could have chemical potential. You could have, you could have stuff in elastic bands. I guess that's spring though. And you could probably think of many other places that humans have figured out to pull energy from, okay?